Compound inequalities are the next topics of conversation. So when we talk about solving compounds, we talk about solving two inequalities with what we call an operator linking the two. Two operators we talk about. One operator is an AND statement, and when the inequality says AND, it means that both statements have to be true. In other words, the solutions must overlap, and we call that overlap an intersection. Another operator used in compound inequalities is the word OR, and OR means that your problem is true if at least one of the statements is true. So in this case, we get a union of the two solutions, and union basically means everything is a solution. We'll go through some specific examples. I know that's kind of a out there kind of explanation, but we'll tie it all together with the problems. So let's take a look at our first one. This is a very simple compound inequality. In fact, the two inequalities have already been solved. It says x is greater than -5 and x is less than 1. So here's that operator of AND. And let's see how this works out. If I were to graph this, then my solution would look something like this. Here's a -5 on a number line, and I'd open circle that, and I would move to the right. Now, if I was to graph on that same number line, x is less than 1, I'd open circle that, and I'd move to the left. Now, in our previous slide, we said that if AND is my operator, then both solutions must be true. In other words, they must overlap. And you can see in this example here with the diagram that I get an overlap between the two numbers. So what I say is I can say one of two things. All right. I can certainly say, well, my overlap is going to be the numbers between 1 and -5. And in order to write that, what I say is -5 is less than x, which is less than 1. This is my algebraic solution, and this is my graphing solution, because I only represent the overlap or the intersection of the two graphs. So in this next problem, we also have an AND operator, and the difference between this problem and the other problem is the two inequalities are not solved. So let's go ahead and do that. Add 3 to both sides. End up with 10 is less than 2x. Divide by 2 to both sides. X is greater than 5. Move to this side, subtract 20 from both sides. End up with -120 is less than -5x. Divide by -5 to both sides. When I divide by a negative to both sides, I must reverse the inequality sign. So x is less than 24. And if I were to take and graph that on a number line, here's my 5. Open circle, moving to the right. Here's my 24. Open circle, moving to the left. I need to represent as the answer the intersection of the two, which goes from 5 to 24, both. And then I need to state that in an algebraic fashion, so I say 5 is less than x, which is less than 24, like so. Moving forward, here's another way that an AND problem is written without really writing an AND. AND is usually talking about numbers in between two other numbers. So this is really like a compound inequality involving an AND. In order to solve this, I can break it up in this fashion, say -12 is less than 4 minus 3x, and 4 minus 3x is less than or equal to 13, which I really don't prefer to do if it's written this way, because what I'll do is I'll just do the same thing to both sides of an inequality. So in this case, I'll subtract 4 to two sides of an inequality. And in that case, I get negative 16 is less than negative 3x, which is less than or equal to a total of 9. And then I'll divide by negative 3 to both sides of an inequality. But since I'm dividing everything by a negative, the inequality signs must be reversed. So in this case, what I have is I have my algebraic solution here, and if I'm going to graph that, I graph negative 3, positive 16 over 3. The negative 3 has an open circle since it's, has a closed circle since it's equal to, and the 16 over 3 has an open circle, and I connect the two dots. Alright. Now, here's a unique problem. Doesn't look unique initially, but let's go through solving it and I'll show you why it's a little bit different. In this case, I'll subtract 9 to both sides. Get negative 2x is greater than or equal to a total of 2. Divide by negative 2 to both sides. Get x, reverse the inequality sign, is less than negative 1. Go over to the other problem, subtract 2x from both sides. Get 3x is less than 9. Divide by 3 to both sides. Get x is less than 3. Now if I were to graph this, then what I'll do is I'll put 3 here, closed circle, moving to the left, negative 1, closed circle, moving to the left. Now, since this is an AND problem, I'm looking for an overlap. Notice there's no overlap between the two numbers. The overlap exists in this region. So we state the overlap as negative 1 to the left, and algebraically that says all the numbers less than or equal to negative 1 are my solution. So there's my algebraic solution, which is a little bit different than what we've seen up to this point. Let's take a look at an OR statement now, and if I were to take and go ahead and graph these two, because they're already solved, I'd have a 4, open circle, and it says x is less than 4, we go to the left, and then I would have a 9, and it says x is greater than those values, so I would move to the right, and an OR states that only one has to be true in order to state the solution. And we talked about this word being union. Now what the union means is it means everything that you see is a solution. So this graph is my graphical solution to the equation, and both of these two parts of the problem are how I state the algebraic solution. Let's go do another one that's a little more complicated. So I have two equations that aren't solved for. I'm going to add 7 to both sides in the first one, giving me a 4x is less than or equal to a total of 32. Divide by 4 to both sides. Get x is less than or equal to 8. And then we have subtracting 12x from both sides. I get negative 9x is greater than or equal to. I get 18. And divide by negative 9 to both sides. I get k, switch the inequality or reverse the direction because I'm dividing by a negative. Get a negative 2. So if I were to graph these, here's an 8. And in this case, I'm going to take and fill that circle in, go to the left. Here's a negative 2. And in this case, once again, I'm going to fill that circle in, and it says k is less. So if I were to graph everything that I see in this particular problem, then what will happen is I see everything from 8 going down forever. So really, I can simplify this statement here to 8 and an arrow pointing to the left. Therefore, my algebraic solution is x is less than or equal to 8. That's kind of a unique problem. We roll through and say we have 2 distribute minus 10x plus 15 is greater than 2. Let's subtract 2 to both sides. Let's combine like terms. That doesn't matter. I'll subtract 2 to both sides. Get negative 10x plus 15 is greater than 0. Subtract 15 to both sides. Get negative 15 is less than negative 10x. Divide both sides by negative 10. X less than, because I'm reversing the inequality because I'm dividing by a negative. 3/2 positive. On this side, I distribute the 2 through. Get 3. That should be an x, not a z. X is less than 2x minus 16. I'll subtract 2x to both sides. Get x is less than negative 16. This is going to be a unique situation as well because I have a negative 16. Moving to the left, I have positive 3/2. Moving to the left, I'm not looking for the overlap or the intersection. I'm looking for what is everything that I see, and I see everything from 3/2 to negative infinity. So my answer is x is less than negative 3/2.